DGI Geoscience Inc. Borehole data with a purpose. DGI Geoscience Inc. was founded in 1997, providing the first commercial service offering of hard rock wireline logging in Canada. Since inception, DGI has traveled the globe, providing downhole logging services worldwide 365 days a year in all climate extremes. In this presentation, we are reviewing advanced geotechnical and hydrogeological applications of downhole surveying technologies. The acoustic televiewer produces a sonar-like image that is highly sensitive to fractures and faults and can distinguish between open and filled fractures. Since televiewer images are oriented, strike and dip measurements can be taken with the click of a mouse. Also, fracture apertures can be measured and fracture frequency to produce RQD measurements. In addition to the oriented image, the acoustic televiewer produces a 360-degree caliper measurement to show the hole shape in true 3D. This can be used for geotechnical breakout analysis or to monitor wear in the paste fill or other linings. The acoustic televiewer can be used to measure structural information in non-core holes, and it can also measure through PVC casing. A full description of structural analysis using both the acoustic televiewer as well as its color image counterpart, the optical televiewer, is provided in a separate video. In this video, we will focus on non-traditional uses of televiewer data for geotechnical and hydrogeological purposes. In regions of high tectonic stress, knowing the stress orientations sigma 1, 2, and 3 and their magnitudes can be of great importance in designing mines and engineered structures. Traditional stress estimation methods are expensive and suffer from sparse data. For example, overcoring data is limited to single-point measurements, which may or may not be representative of the entire rock volume. Tectonic stress interacting with a borehole produces breakouts, which occurs at 90 degrees to the maximum stress acting on the borehole wall. Acoustic televiewer can measure the orientation and intensity of borehole breakout. By integrating breakout measurements made on boreholes drilled in different directions, stress orientation and relative magnitude can be averaged over the entire rock volume. The process is illustrated here. A set of boreholes in the region of interest are selected for televiewer logging. Oftentimes, the televiewer is already being logged in these holes for other geotechnical purposes. After measuring the breakout orientation and intensity in each hole, the observations are fitted to a best-fitting stress model using a Monte Carlo process. The best fit model includes principal stress directions with confidence intervals, as well as relative stress magnitudes. As more boreholes are added to the model, the confidence intervals converge around single points for sigma 1, 2, and 3. In underground mines, acoustic televiewer data has been used to evaluate risk of rock burst by logging in horizontal holes drilled ahead of mining. Rock burst-prone zones have been observed to display some or all of the trends shown in the highlighted interval on the right, all observed in acoustic televiewer data. Fracture frequency and reflective index decrease, with caliper and breakout intensity increasing. Also, hole trajectory deviates strongly in the rock burst zone. While this method does not always predict rock burst, it is a useful analysis that can be done using televiewer data that is often being logged anyway for ground control analysis. Moving on from televiewers, acoustic velocity and density logs can be used to calculate rock mechanical parameters such as Poisson's ratio, Young's modulus, shear modulus, bulk modulus, and bulk compressibility. In the example shown here, the lower rock unit has higher bulk modulus and Poisson's ratio, with lower shear modulus, bulk compressibility, and Young's modulus than the overlying rock formation. Now moving to technologies designed specifically for hydrogeological applications. The borehole magnetic resonance probe is a powerful technology recently introduced to the mining industry for measuring both porosity and pore size distribution from which permeability can be calculated. The results are very comparable to packer, core, and pump tests, but with rapid data availability and high-resolution data continuous throughout the hole. On the permeability log to the right, BMR results are compared with core and packer tests. The packer test results are shown in light green, taken over 5-meter intervals. The core tests are shown as red bars, taken at isolated points. The BMR measurement is shown as a brown curve, and the green stepwise curve represents the BMR data upscaled to the same intervals as the Packer tests. As is evident, the upscaled BMR data is very similar to the Packer tests. However, the native BMR data shows there is large variability in permeability that is not reflected in the Packer data. For example, the Packer test from 42 to 47 meters shows moderately high permeability, but the native BMR data shows the zone actually contains two high permeability zones with a zero permeability zone in between. To the right, the BMR data has been used to calculate the free fluid volume, capillary-bound fluid volume, and clay-bound fluid volume. On the lower left, BMR data is shown in blue, with pump test data shown in black and unconfined core test data in red. The BMR data agrees well with the pump test, while the unconfined core tests are reading higher porosity. Another powerful tool for hydrogeological applications is the flow meter. Flow meters directly measure flow rates and direction downhole and are usually performed under ambient and pumping conditions. Under pumping conditions, reduction in flow rate indicates a permeable zone, and transmissivity can be calculated simply by subtracting the flow rate below the zone from the flow rate above. Several other probes with hydrogeological applications are listed here. Resistivity logs can be used to detect fracture zones, calculate fluid saturation, salinity, and contamination levels. Acoustic velocity logs, discussed above for their geotechnical applications, can estimate primary versus secondary porosity and can be used for fracture zone detection. Gamma and spontaneous potential logs are often used to detect impermeable shale layers, and spontaneous potential logs can detect salinity contrasts. Televiewers are used to image open features, such as fractures, that often act as high-volume flow pathways. Also, televiewers produce high-resolution borehole deviation surveys used for accurate piezometer placement and water level monitoring. Finally, DGI offers several borehole surveys to assess the conditions of the borehole itself. These include gyro and deviation surveys, cement bond logs for assessing the quality of cement bond between casing and formation, important for preventing water migration in the subsurface, and caliper measurements for measuring wear or linings such as paste and shotcrete lines. Finally, DGI offers downhole video cameras for real-time inspection of borehole conditions, casing, screens, etc. DGI Geoscience Inc. Borehole data with a purpose.